Hess law. Hess law, the enthalpy change for the conversion of reactant to products is the same. Use a diagram to explain. We can directly get D from A. The heat absorbed or released is delta HE, and this is the another way to get D. The change heat are respectively H2, H3, and H4. The heat of any reaction delta H for a specific reaction is equal to the sum of the heats of reaction for any set of reactions, which in sum are equivalent to the overall reaction. See an easy example. These two equations, how to add the two equations as one? We should add product together and add reactant together. However, if in the product and reactant they have same compounds, they can be offset. In this example, C can be cancelled. Then reactant add together, products add together. Get the results. Hess law is which states that the enthalpy change of a reaction is independent of the route taken. That means we can add and subtract reactions to obtain the desired result. There are two principles. If an equation is reversed, the sign of the delta H value is also reversed. 2. If an equation is multiplied by a coefficient, the delta H value is multiplied by the same coefficient. And the enthalpy changes we are using should be measured under constant pressure conditions. We should get the question equation by adding or subtracting equation E and equation R. There are an A and a B as the products in the question equation, but in equation 1 there are two A and two B. We cannot directly get the answer by add and subtract the two equations, so we should do some calculate. We can multiply them by a half. And the corresponding delta H also need 2 times R(E). In the question equation, there is an E as the product. But in equation 2, the corresponding E is reactant. So we can let equation 2 multiply -1 to make products and reactants exchange. Corresponding delta H also times -1. We can find these two equations now is same of these two. Use the same way, add them together. Finally, add the corresponding to delta H. The answer of this question HRXN equals 550J. After the two examples, we can conclude some mistakes that students are probably to make. First, using the same units, ensure the enthalpy changes for all the reactions are expressed in the same unit before adding them together. Second is to obey the two principles. The strength of the Hess law is it allows us to calculate delta H for reactions that cannot be measured directly, and the method provides consistent and reliable results when applied correctly, regardless of the choice of intermediate reactions. And the weakness, I think the reactions involving numerous intermediate steps, the method can become mathematical complex and time-consuming. We had better checking computations. Last part, how to distinguish exothermic and endothermic. The simplest way to judge this is when delta H greater than 0, it is exothermic reaction. By the contrast, when delta H less than 0, the corresponding reaction is endothermic reaction. These are all about the Hess law. Now we can solve the question in the task. First, let us number these 4 formulas, convenient to solve the question. Step 1. We look at the POCl3, the product of final equations. Which equation has the POCl3 in these 4? we can find that only in the equation 4 have the product POCl3 corresponding to the POCl3 in the final equation, so the amount of the POCl3 also need to be same. 2 times 5 can get the 10. So that we should make equation 4 all times 5. Now they are the same. At the same time, the delta H3 also need 2 times 5. Second step, the same with step 1. The reactant P4O10 in the final equation, corresponding to the so P4O10 in the equation 2. The amount of P4O10 are same, but the P4O10 in the equation 2 is product. In the final equation is reactant. So we need to change the P4O10 in equation 2 from product to reactant. Let equation 2 all times -1. So that we can let the product and reactant exchange. Now this P4O10 can correspond to it. And then delta H2 also should multiply -1. The third step, look at the PCl5 in the final equation, corresponding to the PCl5 in the equation 3. Equation 3 times 6 can get 6 PCl5, but after multiply 6, the PCl5 in equation 3 is the product. In the final equation is reactant. Therefore, we should let times -6 to instead times 6, that exchange the product and reactant of equation 3. Now, the amount and the position of PCl5 are all the same. The delta H3 also multiply -6. H 等于504 kJ. After rewrite these three equations, we can compare what is enough and what is missing. To determine how to write the last equation, the product and reactant can offset each other. 6 PCl3 and 10 PCl3 can offset each other and there are still 4 PCl3 left. So in the equation 1, there need 4 PCl3 as products to offset each other. We can find that there are exactly 4 PCl3 as products in the equation 1, so we do not need to change anything of equation 1. Now all the PCl3 can completely offset, and all the 4 equations are rewritten. Finally, let us verify it again. The last step, we add all the 4 equations. The 4 delta H also need to add together. The added equation exactly matches the equation in the question. And the final answer H equal -615 K. HRXN less than 0, so this equation is an exothermic reaction.